So we have renamed the respective streams. Then we can specify the seawater condition. You can assume that the pressure at the suction side of this pump is 1.2 bar. Actually, the pressure at certain level of seawater level, let's say the temperature is 35 centigrade, and the mass flow for the initial value we can specify, let's say 40,000 tons per day. And don't forget to specify the mole fraction of the water. We assume that seawater consists of pure water here. Then for the discharge pressure of the seawater outlet, you can assume that the pressure is 5 bar. Then we will specify the inlet and the outlet flat heat exchanger, particularly the cold side. Oh, I forget to specify this one, this pump, Glycol-Water pump. Let's say we want to raise the pressure up to 6 bar. And then we can specify the seawater or flat heat exchanger here. I want to set constraint regarding the seawater that we want to discharge to the ocean, because there is limitation regarding that. So I want to set the limit for the temperature drop for the seawater is not exceeding 5 centigrade, so I want to specify 30 centigrade here. We obtain the temperature of Glycol-Water at 30 centigrade, which is not permissible. Thereby, we will adjust the mass rate of Glycol-Water and seawater respectively to comply the required temperature for respective stream. Then we will perform the adjustment so that shell and tube, vaporizer and flat heat exchanger can meet the temperature constraint. So we can add the adjust manipulator by select this one and put it into our flow sheet. We can adjust the ethylene glycol or Glycol-Water mass rate so that the temperature constraint at natural gas to metering stream can be complied. You can follow me to set the adjust manipulator. We will select the mass rate of the Glycol-Water 1 as the independent variable, and then we will set the natural gas temperature to be the dependent variable. The temperature of this natural gas downstream the vaporizer is 10 centigrade, and we can reduce the tolerance and the step size here. Don't forget to add the iteration number. So we can start the adjust logic or manipulator here. As you can see, the natural gas to metering has already achieved the required temperature, which is 10 centigrade, and we find the mass rate required for the heating process approximately as you can see here. Then we can continue to find the mass rate required for the seawater so that the temperature of this Glycol-Water is 25 centigrade. You can add adjust manipulator here and set the manipulator. So we want to set this temperature at 25 centigrade by changing the mass rate of the seawater. You can specify here 25 centigrade. Then we have find the solution. So actually the mass required for the seawater approximately 70,000 tons per day of the seawater required to heat the Glycol-Water. Then after we obtain the mass rate of the Glycol-Water, we will connect this Glycol-Water number 1 and Glycol-Water number 1 accent by adding the recycle stream or recycle manipulator here. You can move the recycle manipulator icon to the place between these two streams and connect the respective stream, and then the recycle manipulator will calculate the difference of these two streams. So I think to simplify the look of this flow sheet, we can hide the adjust manipulator. Then finally we obtain the regasification system here, and actually this system is commonly found in floating storage and regasification unit due to its compact design, making it preferable to be installed in limited area. For overall heating process, the LNG will be heated by Glycol-Water, and the Glycol-Water will be heated by seawater, and then seawater will be discharged at temperature of 30 centigrade. I think that's all for the simulation of LNG regasification system using intermediate fluid vaporizer. In the next video, we will try to perform integration between the LNG regasification system and the CO2 liquefaction process in order to support the implementation of CCS and CCUS. So I think that's all from me. Thank you for watching this video. See you in the next video.